Hello everyone, welcome to the video lecture series of course Internet of Things. In today's lecture, we are going to discuss fourth unit, that is IP-based protocols for IoT. In today's lecture, we are going to discuss the protocol IPv6, 6LowPAN, RPL. I am Professor Swati Suresh Pawar. Before starting with today's lecture content, let us discuss the content in the fourth unit, that is IP-based protocols for IoT. In this unit, we are going to discuss protocol IPv6, 6LowPAN, RPL, REST AMPQ, COAP, MQTT. Let us first discuss the protocol IPv6. Internet Protocol version 6, that is IPv6, is the network layer protocol which is a successor of IPv4. IPv4 provides 2 raised to 32 addresses, nearly 4.3 billion, but due to increase in the number of devices, globally is causing limitation to the number of IP addresses available with us. This calls for a large address space, which was the initial cause of IPv5 development. IPv6 has 128-bit header length, which provides 2 raised to 128 address, which are far more than IPv4 in comparison. IPv6 provides location, system and identification for computer in the network. IPv4 and IPv6 are not interoperable by default, but some development is in the process where direct communication between the IPv4 and IPv6 is possible via middle level logic. Special features of IPv6: extended address space and scalable solution, plug and play, security, VPN, optimized solution, real-time applications, mobility, extensible. First, extended address space and scalable solution. IPv6 provides 2 raised to 128 address, which is far greater than that of IPv4. Thus, IPv6 provides highly scalable option for devices in IoT environment. Plug and play. IPv6 provides a plug and play mechanism because of which the connection to the device into new network becomes easy. It has a serverless mechanism that provides automatic configuration. IPv6 offers nodes to have multiple IPv6 address on the same network, which allows devices to establish overlay, also called as community of internet interest, that is COI, which can act as separate department or group on top of other IPv6 physical network. Security. IPv6 include end-to-end security mechanism with the help of authentication and payload encryption mechanisms. IPv6 network can adapt to end-to-end security by making compulsory to the end host top secure the data traffic between them. VPN, virtual private network creation, is standard and easier in IPv6 compared to IPv4 and IPv6 as authentication header, that is AH, and encapsulating security protocol, that is ESP. Optimized solution. IPv6 incorporates all the good characteristics of IPv4 and removes unnecessary or unused features of IPv4, making the IPv6 a more advanced internet protocol. Merging of two overlapping IPv4 network is difficult, but same, that is merging of networks, can be done easily using IPv6. Real-time applications. IPv6 uses label flow while giving specifications, which makes the router recognize what kind of packet is being transferred. Mobility. IPv6 delivers a robust and efficient way to provide enhanced mobile IP support, which is very useful for mobile computing devices. This feature is very useful for IoT-based application development as it consists of mobile devices scattered enormously. Mobile IPv6, that is MIPv6, defined in RFC 3775, is under development. Extensible. IPv6 has a scope to be extensible as its format provides a way to add new options. IPv6 supports following type of transmission: Unicast transmission sent to one particular address, multicast transmission sent to every member of particular group, anycast transmission sent to one particular member of a specific group, and this is generally done to the closest routable devices. As one can observe, anycast mode is added in IPv6 which was absent in the IPv4. Addressing in IPv6. IPv6 makes use of 128 bits to represent the address of a device in the network. 8 groups of 16 bits each are prepared to represent an IPv6 address and are separated by the colon character. Each 4 bits in the address is represented by hexadecimal digits ranging from 0 to F. So the group of 16 bit is replaced by a equivalent 4 hexadecimal digits 0 to 9 and A is equal to 10, B is equal to 11, so that F is equal to 15. For example, 2001 as to 0DB8 as to 85A3 as to 0000 as to 3223 as to 0BA0 as to 010 as to 0001. If ending address consists of all zeros like 0BA0 as to 01E0 as to 000 as to 000 as to 0000 again as to 000 as to 000 as to 0000. It can be abbreviated as 0 BA0 as to 01E0 as to. Some more addressing abbreviation mechanisms available with the IPv6. IPv6 packet format. Figure shows the IPv6 packet format. It consists of extension, header and payload, destination address, source address. Above that is the payload length, next header, hop limit, version, traffic classes and flow level. As shown in figure, IPv6 packet format, it contains IPv6 header and IPv6 payload. IPv6 header contains two parts, IPv6 base header and optional extension headers. The optional extension headers and upper layer protocols like TCP are considered as a part of the IPv6 payload. IP header in IPv6 is considered to be of fixed length of 40 bytes. Version field uses 4 bits and signifies the version of Internet Protocol, that is 6 in this case. Traffic class uses 8 bits and is intended for creating, that is origination, nodes and forwarding routers to identify and separate out different classes or priorities of IPv6 packets. Flow label or flow ID is 20 bits field, defines how to handle the traffic. This field identifies which packets require special handling by IPv6. A flow means the sequence of packets which are sent to the unicast or multicast destination. If the host or router doesn't support this field, then the field is set to 0 if packet is being sent and is ignored if packet is being received. Payload length is 16 bit in length and is used to define length of payload in octets and is described by 16-bit unsigned integer. Payload also represents extension header and upper layer protocol, that is TCP, UDP, etc. Next header is an 8-bit field that represents the header appended immediately to the IPv6 header. Table shows the 8-bit representation and immediate header format. For example, for 00 hop-to-hop option is there. For 01 ICMPv4. For 04 encapsulation IP in IP. For 06 TCP and for 17 it's UDP. 51 it shows the authentication and 58 is the ICMPv6. There are many more are there. Hop limit is 8-bit number that represents how many hops a packet can take in the subnet or network before being discarded by the router. Hop limit is necessary to prevent the packet from endlessly looping in the network and is set by the source or origin node. Source address is 128-bit address of the source of originator node. Destination address is 128-bit address of the final destination node or an immediate node. Exchange of data over IPv4 and IPv6 network is a tricky job. IPv6 traffic can be transmitted via IPv4 networks using tunneling method. In this method, wrapping of the IPv6 traffic is done as IPv4 payload data and IPv6 traffic is sent by the encapsulated into IPv4 traffic, making it look like similar to IPv4 traffic. As the receiving end, the traffic is evaluated as IPv6 traffic only. Such conversion mechanisms are methods used so that IPv4 and or IPv6 devices and networks must coexist. Now let us discuss the 6LowPAN. 6LowPAN. The 6LowPAN communication protocol represents the communication done via IPv6 over low power personal area network. 6LowPAN is a network layer protocol. 6LowPAN is designed for lower power devices where communication overhead should be less. Devices with low processing and communication capabilities use this protocol in network layer. 6LowPAN works over frequency range of 2.4 GHz and has data transfer rate of 250 kilobytes per second. 6LowPAN in network layer and 802.15.4 in link layer works together and describes compression mechanism for IPv6 packets for communication in LRWPAN. 6LowPAN encapsulates IPv6 long headers in IEEE 802.15.4 small packets and are not allowed to exceed 128 bytes. 6LowPAN specification provides following core features: different address length, low bandwidth, low consumption, different topologies including star or mesh mobility, scalable networks, long sleep time, and unreliability. 6LowPAN has the tackle following key issues to make it as a low power protocol. Header compression. LowPAN is supposed to be consuming less power but having large packet size lead to loss of energy. IPv6 header requires 40 bytes of storage. Compression mechanism is must to save the energy with the IPv6 and LowPAN, that is 6LowPAN. Packet fragmentation and reassembly. Patches transmission is in network consumes energy. Packet transmission in a network consumes energy. Larger the packet size, higher the energy requirement. So making it packet size was needed, and low packet size also reduced the chances of packet loss, especially during the use of lost network like 802.15.4. Reworking of neighbor discovery defined in RFC 4861 and 4862 so as to meet low power requirement. Availability of mesh under routing done by the 6LowPAN adaptation layer. 6LowPAN currently defines following headers: the mesh addressing header, hop by hop processing header, destination processing header, for example fragment header, payload transport header, that is for example IPv6 compression header and UDP compression header. The first byte of each header identifies the type of header called as a dispatch byte. Along with the above explained type, additional types can added to 6LowPAN and space is available in dispatch by for further development. Figure shows the 6LowPAN header with dispatch byte. As shown in figure above, each header starts with a dispatch byte which represent which type of header is going to be used. Table shows the byte content and the header type. For 00 byte, not 6WPAN. For 01, IPv6 compression header. For 10, it's a mesh header. And for 11, it is fragmentation header. Mesh header. In mesh, under routing done in 802.15.4, source and destination address of each hop needs to be specified in 802.15.4 MAC frame. Mesh header provides a container to keep original and final 802.15.4 addresses. IPv6 compression header. IPv6 compression is necessary in 6LowPAN to reduce the energy consumption associated with original IPv6 header. Various methods are implemented in this approach. Creating an IPv6 unicast address from EU 164.802.15.4 address in which a standard 64-bit address is converted into 16-bit short addresses. SC1, that is header compression 1, compression format for IPv6 header, and SC2, that is header compression 2, compression format for UDP header were available but are now replaced by a new SC compression format for IPv6 header and NHC, that is next header compression. A recent approach hash content based compression called IPSC, in which selective compression of IPv6 flow labels. IPSC sends compressed IPv6 fields, recompressed IPv6 fields, NHC header in sequence. Fragmentation header. The first fragment defines fully resembled packet in tags for datagram common to an IP packets. This can be used by the receiver to identify fragment belonging to the same packets. Following to the first fragment, rest of the fragment describe the offset of the next fragment in the full IP packets. Now let us discuss the RPL. IETF in 2008 formed a group called Routing Over Low Power Lossy Network, that is ROLL, which create IP level routing protocol for IoT requirements. In 2011, they came up with RPL, that is Routing Protocol for Low Power Lossy Networks. RPL supports IPv6 communication over low power lossy network, that is LLN. RPL supports point-to-point from central server to server nodes on LLN. RPL specification is developed keeping multi-point to point, that is MP2P, and multi-point to point P2MP routing. RPL routing builds a destination-oriented direct acyclic graph, that is DODAO. DODAG has a single root node with no cycles and only one route from each leaf node to the root using which the traffic from the node is routed. Multiple concurrent RPL instance might work in particular network, and each instance is identified by RPL instance ID. Initially, a DODAG information object, that is DOR, is sent by each node that advertises itself as the root. Figure shows the RPL DIO based object. G, that is ground flag. MOP, that is mode of operation. For example, 000 no forward routing, 001 no sorting mode, 010 storing no multicast, 011 storing with multicast, etc. PREF, that is DODAG preference. DTSN, destination advertisement trigger sequence number. Once the message is spread throughout the network, the whole DODAG is progressively constructed. Communication. The node sends a destination advertisement object, that is DOA, to its parents for starting the communication. The DOA is circulated to the root and the root decides where to send DOA considering which the destination node is. If a new node wants to connect to the existing network, it sends a request called as a DODAG information solicitation, that is DRS, to join the network. The root confirms the connection of the new node by accepting the DRS and replying back a DOA acknowledgement, that is DOA ACK. RPL nodes can be stateless or stateful, but usually it is stateless. A stateless node keeps tracks of only its peak complete. A DODAG is only known to the root. The communication go via the root in all the cases. In case of stateful node, it keeps track of its parents as its children. Hence, when communication is going on inside subtree of the DODAG, it is not necessary to go via the root. Figure shows the IPv6 RPL control message. Code field options. Table shows the code and their meaning. 0x00 means DODAG. 0x01, that is DODAG information object. 0x02, that means destination advertisement object. 0x03 means destination advertisement object acknowledged. 0x80 is the secure DODAG information solicitation. 0x81 is the secure DODAG information object. 0x82 is the secure destination advertisement object. 0x83 is the secure destination advertisement object acknowledgement. 0x8a is the consistency check. RPL makes use of the security field after the 4-byte ICMI message header to provide different security options. Security field specifies the cryptography algorithm used to encrypt the message and the level of security needed for the communication of that message. RPL supports various security options like protection against replay attack, semantic security, data authenticity, key management, and confidentiality. There are 3 levels of security in RPL: unsecured, pre-installed, and authenticated. Various RPL attacks are also possible like denial of service attack, wormhole, sinkhole, Sybil, selective forwarding, hello folding, black hole, etc. ASD protocol in network layer. Summary of today's lecture. In today's lecture, we discussed the protocol IPv6, 6LowPAN and RPL. Thank you.